Okay, hello everyone, and welcome to another seminar of the Computational Humanities Research Group series, seminar series at King's College London. Today, I'm very happy to be introducing to you Dr. Nevio Dubbini, who has a PhD in applied mathematics and is currently research fellow at the University of Pisa and CEO of Miningful. Miningful integrates AI-based predictive systems into companies' production, commercial, logistics, and distribution processes. Miningful also supports scientific publications and research projects with statistical machine learning and AI expertise. Nevio is an expert in artificial intelligence, working at the intersection of AI and archaeology to advance the analysis, classification, interpretation, and visualization of archaeology data. He has contributed to major European projects developing innovative methods for predictive archaeology, digital documentation, and automated artifact recognition. And his long-term goal is to understand the mechanisms that enable the prediction of future events, exploring how predictions emerge from information, pattern recognition, and the temporal structure of data, and how they generate new knowledge. And we met many years ago in Pisa when we were doing our PhDs, a very long time. So really happy to have you here and to listen to all you have to say about your project and today's talk, Human in the Loop, AI for Knowledge Extraction from Archaeological Legacy Documentation. So thank you very much, and over to you, Nevio.
Thank you, Barbara, for the presentation. Hello, everybody. I start sharing my screen. Welcome, everybody. I share the whole screen, so since I would like you to see not only the presentation, but also something else. I try to keep it 40 minutes. So from time to time, I try to, just a moment. I'll look at the watch. So I'm going to talk about this project for knowledge extraction from archaeological legacy documentation, which was part of Italian cascade from a European Union cascade funded project, carried out together with Professor Gabriele Gattiglia and in general with University of Pisa, which provided the data and the knowledge, the bridge knowledge for all the analyses that done. Just presenting myself is, even if Barbara just introduced me a little bit. So I came from a mathematics degree and had 3 postdocs, 2 postdocs and a PhD, different areas, but start working in what today call artificial intelligence or machine learning, that at the time was data science, basically, or data analysis, basically applying mathematical modeling and then machine learning to different areas like robotics and neuroscience. Since 2013, can you confirm me you see my pointer?
Yes.
Okay, all right, this is my mouse. Since 2013, I started working in and together with in archaeology and together with archaeologists with a project funded by Regione Toscana, trying to predict archaeological potential in a urban area. And so my experience within archaeology is since that year, basically. And yeah, I'm going to talk about knowledge extraction. So I'm not one from a linguistic side. I'm not one from archaeology side. But anyway, we'll talk about knowledge extraction from archaeological legacy document. In 2018, I founded Miningful, that basically working to predictive AI, and since the last year I'm also a research fellow at University of Pisa. The problem we're trying to handle here is related to legacy documents that basically are a set of reports, notebooks, or also correspondence, this legacy data, which is data that never sees real publication or share of in general. And since some time ago, it's usually locked in analog format. Now many people start to digitize those documents, but digitize, of course, means many different things. And so at the moment, you usually find PDF or image file like JPEG or PNG that include the text or the figure or the information. So the main problem, as you can imagine, is the lack of machine readable data. That of course limit the possibility to access the material or to query the material. Of course, the best possible in terms of results, the best possible digitization is the manual one, but it's prohibitively expensive and time consuming, and also may require a very specific domain knowledge. The source I'm going to talk about comes from this Mago project, which you can access through the link on the top right or through the QR code. They basically include, not going into detail with this very large data lake, they basically include many archaeological documentation of different type, including SP photographic archive, paper archive, and in general other documentation. What you can see here, the size of the documentation, so it's quite a big, although local, it's quite a big data lake. And the Mago project collecting this information and already still collecting this information, are collecting those data from basically some province in Tuscany, like Pisa, Florence, Pistoia, Prato, and Lucca. What we are more interested in this case, in case of our work, is the intervention record. So basically what we try to do is to extract information for filling the intervention record from legacy documents that was reports about excavation. This, I have to say that this is just one of the possible layer of information that you can access, because you can go in many different layers of information, for example, by going into different level of archaeological finding or into geospatial information like geographical or GIS coordinates, polygons, etc. In this case, we are trying to extract textual information from a report of excavation. And basically, what has been already done in Mago, which is something that let us compute accuracy and have a very good comparison with the data extracted. We try to extract the fields that fill this intervention record, that include information like generic information, chronology, description, etc. Will be more precise in the field we extracted. Some of these fields have controlled vocabularies, other are basically free text, and I will be more precise on that in the following. So the project called Archive was within which this work was done was run in 2025. Actually started in April, so it's a work carried out in 8 months, and was funded by the PNRR through a cascade call from the Extended Partnership Future in Artificial Intelligence, so FAIR. And here you can see the input, output, and constraint. The input was documents that was textual and visual. So in the sense that the document can be both plain text, searchable text, or images, can be also typewritten or also handwritten, and may contain both text and images. Usually the documents are not very high quality, can be, as I said, typewritten or handwritten, and in general there is layout noise. And probably from the linguistic point of view, the main feature is the very difficult document understanding requirements. It's usually difficult to understand the information to be extracted unless you are an expert of the sector. And instead, the output schema is to basically try to convert unstructured text into queryable information. These are basically entities and some semantic relation between those, trying to map in them also to standard domain ontologies, which in this case were developed before the project from the MAPA lab. One important feature of the data are I try to describe in this way, zero annotated training data, in the sense that no part of sentences or speech or text was really annotated, but basically the whole or most of the database has already the manual output already available. Okay, so the situation in this where we are in is all the output most of the output was already extracted, but nothing was annotated. At the moment, the technique of extraction, plus some details that I will add later, is extraction without supervision using programmatic large language model, and a very important focus on human in the loop, because one of the main objective in this work is to first try to make the task of the extraction of information easier by the human operators. So this is a basically workflow overview, which I'll explain in detail step by step. At the beginning, of course, there is the pre-processing and the OCR steps. And the OCR was made with typical classical standard tesseract, but combining it with Vision and LLM, trying not to use, I mean, sometimes tesseract was not enough in order to convert images into machine-readable text. Then the second step was extraction of information, which not directly use a large language model, but also made a step with natural language processing, based to highlight the most probably important chunk of documents, and I will tell why. Then the design of the human in the loop framework, including confidence scoring, traceability, etc., in order to extract the fields that are required to fill the database. Okay, so this is instead an overview of the software. So as I said, OCR and the Vision LM was used in first to extract test, and of course Vision LM is slower and resource intensive, but many times was necessary, and is also able to get the right areas of the document even in presence of images or tables. And the general principle is that all the computation that can be handled by simple algorithm, including OCR, do not use large language model. So, for example, in order to extract test OCR test accuracy at the beginning, if the results are not good, then Vision LM is called. For complex problems or requiring intelligence, large language model were used. Depending on the hardware we had, we were able to change the model we bring in. We run everything locally. So as for the effort needed, that was a long time trying to get the right configuration for the right model. But basically, we tried a Google Gemma 4 billion parameters on a computer with 16 gigabyte of virtual RAM GPU, a 27 billion parameter on a server with industrial grade GPU NVIDIA A100 that was hosted by the hosted by the University of Pisa. We tried also the open source GPT. It was basically middle ground between the two, from OpenAI 20 billion parameters. The interesting thing that I will talk about it at the end of the talk. Basically, there were no big differences in performance, even calling very powerful or not very powerful model, and this is probably down to the probably due to the pre-processing step by the natural language processing algorithm. Okay, OCR basically get this accuracy or error rates in terms of character was about 4%, in terms of words about 15%. This is approximately because it was completely human control, so just on random chunk, we tried to understand what was the error rate. But of course, the extraction of information depends on error rate, not in a very strong way. So this is completely acceptable error rate. And coming to the more details, what we do for extracting and preparing information for the large language model is to start with using Tesseract that breaks file into text chunks for granular processing. And after that, we used, in this case, an Italian discriminator large language model just to understand if what is extracted. Oh, I forgot to say, probably was obvious, but so I'm talking Italian discriminator, etc., because the language of the document was Italian. Okay, so the second step was to understand if what extracted by OCR is Italian language or random character or random words. If you try to extract or copy text from PDF where messy images or table are in, you could easily imagine what you get from. And this is basically random text. So in case this is this does not look as Italian, then the Google Gemma, so the Vision LM is called. Otherwise, it is not. A very interesting, I heard about it just few weeks ago. Very interesting approach and very simple. So tried in this respect is not trying to understand if there's the language you are find and then call the vision LM, but just let any large language model correct what you get from the tesseract. According to the speaker I talked to, even on very messy cases, it was the large language model is usually able to give you the right test. So I understand words even if they are very, very messy. So this is something that we should definitely try. Okay, so if the OCR is not working from tesseract, the Google Gemma Vision large language model is called an extract test. Documents are chunked into smaller segment, and here the named anti-recognition models find basically the tasks, the chunk that are archaeologically dense. Okay, and only these chunks are passed to the LLM for extracting information. Okay, that was the natural language processing mid step. Okay, once we get the chunk that probably are archaeological dense of information, we use programmatic large language model through this library that's called the SPI, which basically auto-optimize the prompt based on example you provide. So basically you define at the beginning a signature. So what do you want, the task, and you have to provide some data. So data means example, and the prompts are auto-optimized in order to get the right answer for the data you provided, for the example you provided. Of course, these optimized prompts are what you then use for extract information. Another very not really easy point, at least for us, one of the main feature of this project is that I tried to do something that is useful for the final end user. So extract many different things that, technically speaking, are very different. So we have to put together many different bricks, including those for evaluating the results. And depending on the type of field we're extracting, we use the large language model as a judge, basically ask to semantically evaluate extraction quality, comparing to the ground truth. Of course, this is more related to the free text, where exact matches are. Basically, you need to understand the meaning. Sometimes, usually, for example, the summary, the BERT scores are embedding space code have been used. In case of composite field composed of subfields, a weighted score I use it. Or if any more complex algorithm can be skipped, the simple string matching will use it, for example, for here in our multi-class fields in general. These are the fields extracted from a single document. So what we call administrative area, I excuse myself with archaeologists, if there are any, probably the terminology is not exactly the right one, but we try to associate it with the database fields we want to fill. So basically where the excavation has been carried out. In this case, we need the municipality and the province. Performed by, so who performed basically who wrote the report, name and surname. The document classification has multiple choice, so excavation report or other kind of, there were 5 choices for the type of document. The site classification was just a relation or multi-layered site, just 2 choices. The site details was free text about address and place of intervention. This was one of the most difficult to evaluate. Intervention date, only the year. Intervention and supervision is the person or the person who coordinate or supervise the excavation. And the archaeological findings that have been discovered, described in the excavation associated to those chronologies. So chronologies are dates, archaeological period of the findings. The evaluation for this part was done after normalization, so trying to get different things named the same thing and the same way, plus linked to some canonical identifier. And you will see we just at the moment identify medieval, Roman, modern, etc., the archaeological period named. And last but not least, the summary, that of course is free text. This is the result we get in red, let's say here, and in together with this is the accuracy. Okay, so moment we are focusing on accuracy, simple accuracy. So how much you get right from your extracted. And if you see weighted, it was the evaluation, the way they are evaluated. So weighted score, exact, strict matching, LLM as a judge. And these were completely evaluated by humans. So to understand if the findings and chronologies that were in the excavation was acceptable or not. Of course, some fields are more easy to extract, some things are not. But probably the best, at least from a practical point of view, that was one of the aim of the archive project, is we point to is a big reduction in validation time. So the basic idea is that from now on, you don't read the report, fill the database. So you let the software fill it for you, and you can check in many different ways, and we will see if the information are the good ones. Okay, so it's a good, a big reduction in validation. And that's the human in the loop side. So we'll see many pictures in a minute where we created an interface, so a web application where you don't see just the field extracted, but we provided confidence score. So not only what is the information extracted, but also how much the large language model itself consider it robust. Technically speaking, it's computed on a token base with basically the log using the sum of logarithm of probability of the predicted token. In this way, it computed the confidence score. So if some token is much more likely, much more probable than other tokens, the confidence is high, otherwise is low. This confidence score are also used to flag, to warn some extraction, since when they are lower, you can decide to raise a warning to say yeah, this is the field extracted, but maybe you should check it. In the interface, you can select what is the field and highlight the text lines in case of searchable text, or just a page where the source document enables where to look for the information it is extracted. If some data is missing, there's an automatic warning. The user can edit, confirm, or reject the extract and the extracted entities. And there is also the possibilities still already available to see all the reasoning by the large language model. So we try to give the user any possibility to check, but just get the data and try to check it fast. What we are doing, so it's not complete at the moment, is to refine semantic domain ontologies and taxonomies to use to check consistency, terminology, and relationship, because there's a big problem in here, because many places or in general terminology is different from the same things from the different period, and so there's a not an easy to get language problem. And we are also developing some continuous learning algorithm in order that correction are used as new input and labeled that are now not present. Before looking at the interface, now I have many screenshot. I would like you to see a couple of documents.
You're muted now.
Sorry. Oh, yeah. Can you hear me again? Yeah, thank you. So I was saying, I'll let you see a couple of documents. This is a very well formatted one. So the text is searchable in this case. You can see, probably you don't have to see all the details, but basically the text is searchable, but the document is filled together with images, maps, figures, etc. And so this is 30 pages, and the biggest document was about 400 pages. This is basically an excavation report written in, I think, Microsoft Word or similar. Or you can also have this more older document, which was typewritten with the stamp images, and also the other thing that in this case was digitized by using a scanner probably. And you see the difference also of the written text in the two cases. We explicitly at the moment leave out the handwritten document. So document can be this can range between a very well formatted one and something that is really different. And now I should share again. Oh no, I'm still sharing. So I have to make the presentation again. Okay. Just to let you see how it is run. Basically, now if you click on here, you should see that the relevant chunk of text is highlighted, and that's where the information is. You can see the confidence. You can edit in case you want the extraction. And it's written also the page and the extracted data. And this is for every field. Performed by, in this case, the document classification. In this case, it's interesting to see that The highlighted pages was, you cannot see the whole page, but it was the page 11, where there is no direct mention to a real excavation relation, archaeological excavation report. But basically, the extraction was done by understanding the meaning on what was found and what was written in the page. So site classification can be just two fields, so site, multi-layered excavation site, and site details are also the address, so the exact place where it is, the excavation is carried on. This is exact, but of course, from here to get something that can be compared to another field that just, report, for example, San Rocco Church, or something that is called a little bit differently is very challenging. And also we had this problem also for the address. The intervention date in this year, the intervention supervision here, etc. And the findings. At the moment, you will see some here. Some text is highlighted, but in this case, a very technical thing at the moment is that, of course, the different findings are throughout the document. So it's not easy for a single field to point to the exact area. There's no one area of the document for all the findings. So probably we should let the user be able to click every finding and point to the place where it is found. But even if we do that, the same finding can be probably mentioned in more than one part of the document. And so this is some technical issue we're trying to solve. Associated with each finding, there's the chronology, so the archaeological period. In this case, we try to normalize it just to saying the period, so Roman, medieval, modern, etc. Well, we could do this, so everything is transformed from 17th century to a certain period, 13th century, or any date. But of course, we could do also the other way around, depending on what is needed. And the summary. The summary that is compared to the actual summary already written manually by the users, with accuracy depending on an embedding. Okay, this is the same thing basically for the other document. These were very well extracted. The site details is exactly what's written here, and it's exactly the right place. But of course, for example, going from here to a place on a map, it's going to be very challenging, and this is something that it is not done at all at the moment. Okay, this work basically about the same, not exactly as well, but even with written text is extracted in a meaningful way. Coming to conclusion, which I like to call challenges. So regarding the future work, and if you have, of course, any question or feedback, I would like to, or general comments, I would like very much to hear from you. There are some obvious challenging, and written document remains excluded from OCR. Computational resources the access to the, for example, to the powerful AI of the GPUs from the University of Pisa, or if you need to buy it and if you need to use it, it's not that simple. And this is something that you have to take into account every time you use it. It's a lot of computational resources, used or wasted in some case. And in general, the project had many different information to extract that probably will be treated specifically. Each case is very different from the other. From specific challenges, one is the evaluation complexity, which we try to address by using LLM as a judge. But for example, place names may vary across historical period or local usage, and so probably addressing it by tagging the different place name in different documents to get together with some term taxonomy, but it's not easy to address things that way without reading the document. Okay. The other point that was mentioned at the beginning, probably, basically we use the natural language processing to highlight dense archaeological texts, and only those are passed to the large language model. This was done for a very practical reason, because for a document of 100 of pages, it was basically impossible to give it to the large language model to be analyzed, since these documents are 8,000. So it's to make computation basically possible. But we noticed that now, since basically the LLM just see the intermediate chunk extracted, you can use very powerful one or not powerful one, and basically the accuracy of the results are the same. So we are faster, but we are not using really the power of large language model. And we are also implementing a repeated large language model application for the same field. So basically the same field is extracted 3 times or 5 times in order to get some measure of variability of the field, and in order to get the answer, for example, the most repeated one. So basically to have a more robust answer in order to, of course, avoid hallucinations. Okay, I'm open to your question if you have any. Thank you.
Thank you very much, Nevio. Okay.